Hey, Algebra 2 students, this is Mrs. Bird. I am looking at Algebra 2 Project 1, the part that is being presented to you in Lesson 3. So we're going to start out with a little bit of background information, and then I'll walk you through some tips and tricks as we answer the questions presented to you in this Lesson 3. Okay, so starting out, we got a little bit of background information. We still have Wizard Engineer. Helping out Princess Polly and Prince Digit, solving more math problems about the air conditioner, continuing their quest to gather information. Polly and Digit come across the servant in the castle who's having the whole castle repainted. So now we're switching away from the air conditioning to discussing the castle being painted. So down below in this next paragraph is where we're being presented information about the painting of the castle. The servant says that it will take X days for the first royal painter to paint the dining room of the castle. So I'm kind of making note of that. We're painting a dining room with one person that will take X amount of unknown days. But he says if he works alone, it will take X days. And it will take Y days for the second royal painter to paint the same room himself. If the painters work together, they can paint the dining room in 12/7 days. So to break that down is that we're painting a dining room and we have a possibility of two painters working together. We have X days for one and Y days for another, but we know if they work together, they can paint that in 12/7 days. So keeping in mind, we just have some information regarding the dining room. And then in this next sentence here, it says it will take 2 times as long for the first painter to paint the ballroom. Okay, now we have a whole nother room of the castle being painted, and it's taking it twice as long for that first painter, and it's taking the second painter 3 times as long for the second painter to paint the ballroom. So a lot of different things going on. We have 2 different rooms, ballroom and the dining room, and we have 2 different painters. So the first thing that comes to mind here is we have 2 different variables, X days for the first painter to paint to the dining room, and then we have Y days for that second painter to paint the same dining room. 2 variables. I'm thinking to solve this, we need 2 equations. Since it's a system of equations, to solve 2 variables, you need 2 equations, which is indicating a 2 equation system of equations. Whew, I was struggling with that wording there. Okay, so with all of that in mind, that is actually number 1. Which system of equations represents this situation? So in other words, I'm going to work on setting up the system of equations. So I need all of that information. Let me just make this a wee bit smaller. So I'm going to use all of that information, but I have information presented to me about 2 different things. We have information about the dining room. Oh my gosh. STR Uglin. Okay. We have information about the dining room. And we have information about the ballroom. So those 2, that's going to classify my 2 equations. Everything involving the dining room is going to be in 1 equation. So let me just first identify all of that information about the dining room. We have 1 painter that takes X days for that ballroom, for that dining room. And then we have another painter that will be Y days. And we know if they paint together, it will be 12/7 days total to paint just the dining room. So I'm going to make some notes on that. X, I'm going to put that over a 1, and there's a reason for that in 1 second. X is the amount of days that the first painter, it will take for him to paint the dining room. We'll call him painter 1. So the number of days painter 1 takes. What does the 1 mean? For 1 dining room. But we're going to be asked to solve for how many days it will take the first painter. So we're going to be asked to solve for x, which means I want to figure out that 1 dining room, how long is it going to take for him to paint 1 dining room? So how many days? X days. 1 dining room per X days. So maybe we're just going to flippity flop that. So instead of saying days per 1 dining room, we want to solve for 1 entire dining room over X amount of days. And we're going to do the same thing for the Y days. That is days over 1 dining room, but I'm trying to solve for 1 entire dining room, so I'm going to have 1 dining room over Y days. Now, the reason why that becomes really important is because now when we start working together, painter 1 is working at a rate of 1 dining room over X amount of days, and X can be 3 days, 3/4 of a day, but he needs to paint 1 entire dining room. And he's working together with the second, who works at his own rate of 1 dining room per Y days. Y being however many days it takes him. And they are completing that in 7 days, or 7/12 of a day. So that is my equation to represent the dining room. But now we have the ballroom information, and it says it will take 3 times as long for the second and 2 times as long for the first painter. So remember, my first painter was the X. So now all of a sudden I get a ballroom taking 2 times the amount of days as it did for the dining room. Adding that with the rate at which it is 3 times longer than it took for him to paint the dining room. And that's going to be painting 1 entire ballroom per 4 days. So in other words, a lot of these will look like they are reciprocals of the way that it's presented there. Hopefully that it kind of explains why we would be seeing the reciprocals. But reach out to me if I didn't clarify that well enough for you. So here's our system of equations. That main takeaways here is that first equation represents all the information about dining room. Second equation represents everything about the ballroom. Okay, I'm going to pause the video before I attack question 2. Okay, so for question number 2, we're still now using that systems of equations that we wrote here, and which observation is correct about the system. So all of these have something to do with the solvability of the system of equations. So to solve a system of equations, you need at a minimum the same number of equations as unknowns. So here I have 2 unknowns, x and y, which means I need at least 2 equations, which I do. So this one, it is potentially solvable because the system has an equal number of equations and unknowns. It's only potentially solvable because we sometimes have things like extraneous solutions. We don't know enough about the equations quite yet, but we do know that we have the potential of solving them because of that 2 variables, 2 equations rule. So that's question number 2. And then questions 3 and 4 is getting us to actually start solving the systems of equations. And we're going to be using the method of substitution. And we're first going to isolate the variable x within this first equation here. So let me clean things up a little bit and I'll start to solve that. Okay, we're back with question number 3, which is asking us to start on the process of solving that system using substitution. And we're going to be taking this first equation here and solving it for x equals. Now, again, we still have that variable of y, so we're not going to solve it to a number. It's not going to be something like x equals 7. But we're still going to have an expression. It's going to have an x equaling something with the variable of y in it. So main goal here is to just get x by itself. So as I look at this, the first thing that really kind of jumps out at me is that there's a ton of fractions, right? So my first trick would be to get the x out of that fraction. So how do I move this x out of the fraction? Well, I know that if I multiplied that by x, x times 1 over x would be canceling out, thus getting it out of the denominator. But what I do to one side, I'm going to do to the other. And you know what? While I'm here, I'm actually going to multiply by a y as well, just because I'm going to be cleaning up that 1 over y fraction, essentially getting rid of both of those fractions in one swoop. So I'm going to be multiplying by the common denominator between x and y, which in this case is xy. So when I multiply, I should get a y plus x is equaling 7 over 12 xy. A lot cleaner looking, right? So now I see two variables, or I'm sorry, two terms. Whew, two terms with an x. So I'm going to move those to one side. I'm going to move the x to the right-hand side, which means that I would have been subtracting the x over. Now, the benefit of that is because I see a common factor. Both of these terms have an x, which means I can factor that x out. So now I got 7/12 y minus 1. I almost forgot the minus 1 when I was doing that earlier, so don't make that same mistake. And then as messy as it is, I still only have that one variable of x that's multiplying with this whole mess. So I just need to inverse that multiplication, which would be dividing. So I'm going to divide everything by that 7/12 y minus 1. And when I divide that by this side, they would cancel out to just leave me the x. Now, this is perfectly correct. We have done what it's asking for and gotten x all by itself. However, there is something still kind of messy about that fraction right there in the denominator. It's kind of like a fraction and a fraction. So I'm going to just simplify that ever so slightly. And to do that, I don't like the 7/12 thing. So I'm going to go ahead and multiply that by 12, because then at least it's going to get rid of that division of 12, that fraction piece. But I also have to multiply the numerator of y by 12. The reason for that is because what is the value of 12 over 12? It's value of 1. So when we multiply by something that has a value of 1, I'm not changing the actual value, right? 3 times 1 is still the exact same value of 3. So here, multiplying 12 over 12 is 1. So I'm not changing the value of whatever this blue expression is. I'm just going to change the way it looks. So to do that, the numerator becomes quite simple. I would just get a 12y. Denominator, we do need to use that distributive property because I have two terms here in the denominator, but 7 divided by 12, so division of 12 multiplying by 12, benefit of that, no more fraction. And then we got 12 times that -1. Okay, so this is a simplified of a response for x that we can get. So that is question number 3, solving for x. Okay, now we're back with question number 4, which is asking us to continue on our solving by substitution route to be able to solve for y. So we still have our system of equations here. And remember, we took that first equation and we solved for x. So now I can take that value of x and use it to substitute into that second equation. So I'm going to pull this second equation, and it will take up quite a bit of room, so let's make sure that you do give yourself enough space. And before we do anything, I'm going to make the suggestion of simplifying this system to begin with. Right now, if you took this fraction and plugged that in, you would have a fraction within a fraction, kind of gross. So I might suggest that we clean this up by getting rid of all the fractions. And we're going to do that by multiplying by this common denominator. So 2 times 3, common denominator there would be 6. And then we have an x and a y, common denominator there would be an xy. So I can multiply by 6xy, but I'm going to be even fancier, and I'm going to multiply by a 24xy. Now, why would I be multiplying by a 24xy? Because 24xy is the least common denominator between 2x, 3y, and the 4. So by multiplying by the common denominator for all 3, I'm getting rid of all 3 fractions. So to multiply here, I would get 24xy divided by 2x, which that's just going to leave me with a 12y, plus 8x equaling 6xy. Okay, so again, no more fractions. A little bit cleaner, right? Now we can start our substitution, which is quite a bit easier. We're going to take our expression of x, and we're going to plug that in for every x variable that I see. So I get 12y plus 8 times 12y over 7y minus 12 equaling 6 times 12y over 7y minus 12 times y. Okay, all I've done is substitution. Admittedly so, it's starting to look kind of scary. It's starting to look a little long. But if we start to just simplify things as best as we can, chunking it piece by piece, it will start to look a whole lot nicer. So the first thing that I see is I have this 8 multiplying with a fraction. If you remember to multiply fractions, we just multiply straight across. So I have 8 times 12y. Not changing that first 12y at all. So 8 times 12 is 96. And that denominator doesn't change because 8 was just over a 1. 7y minus 12. Okay, we can do the same things here. And in fact, we can kind of do them all at once. We have 6 over 1, so I'm going to multiply 6 with the 12, and then 1 with the 7y, and then we're going to do the same thing with the y. Multiply the y with the numerator, and then the 1 with the denominator. So first things first, we got the denominators. That's not going to change because I got a 1 times 7y minus 12 times 1. So that one's pretty straightforward. 6 times 12y is 72y. And then 72y times y becomes a 72y squared. Okay, we're still just in this simplification process. Okay, simplifying, we can see some fractions here. And I have two fractions with the same denominator. So maybe you want to think about multiplying by the LCD again, which would be 7y minus 12. And again, just by multiplying by the LCD is going to be getting rid of your fractions. So if I take this piece and I multiply it by 7y minus 12, what I do to one side, I do to the other. Now, the only trick here is that please don't forget to distribute. So I still have that 12y that is multiplying with that LCD. But then the 7y minus 12, when I multiply it with this second term, we get canceling. That's a big benefit, no more fractions. Multiplying and division are inverses, they cancel. Okay, so as a heads up, if you ever see fractions and you want to get rid of them, multiply by the LCD, multiply by that common denominator, and it will go away. Okay, still a little long, but at least there's no more fractions. I do see some multiplication here, so I got to use my distributive property again. 12 times 7 is 84. That 4 looks funny, and I think that it's a 9. 84 y squared. And then 12y minus 12 is a negative 144 y plus 96 y equaling 72 y squared. Okay, I'm running out of room, so let me pause and clean things up, and I'll be right back. Okay, and I'm back. I've just cleaned it up a little bit and given myself just a little bit more space. Still just picking up where we left off. As I look at this, I'm starting to notice that I have a quadratic. I have 84y squared, and then another common like term over here with the other y squareds. So I'm going to use my solving of quadratics skills. And first thing I need to do is set this equal to 0, and I might clean it up a little bit by combining those like terms. So I'm going to subtract 72y squared from both sides. And then if my subtraction is good, I get a 12. And then I do have these common terms here. 144 plus 96 is a negative 48y equaling 0. So as a reminder, to solve quadratics, it has to be equaling 0 because we'll be solving for that x-intercept. So looking to the left-hand side, I can factor this. It's just a binomial. I'm noticing a common factor of 12, right? 12 goes into 12 and 48, and then y. So I'm going to factor out that common factor of 12y. I'm left with the y minus 4 equaling 0. Okay, my favorite property in all the land, ZPP, says that if you have two factors equaling 0, then both set them equal to 0 and solve. Divide both sides by 12, we get 0. Add 4. So 2 answers, but only one of them makes sense. Remember, y was the number of hours that it takes the second painter to paint the ballroom. Or was it the dining room? I think it was the dining room. Either way, the painter is painting. Does it make any sense for him to paint the ballroom, all of it, in 0 hours? That doesn't make any sense. In 0 hours, he would not have even begun. So there's no way for him to finish. But it does make sense for him to have painted the room in 4 hours. So again, this is the second painter. Takes 4 hours to paint the dining room. I'm pretty sure it was the dining room. Wasn't it the dining room? Okay. So that is question 4, solving for y. Okay, so picking up where we left off with question number 5 was to use all the information that we have so far about the system of equation and use substitution to solve for x. Let me clean that up. So in the previous question number 4, we found that y is equal to 4. And here's our system of equations, and we're going to use substitution to plug that bad boy in. Now, to plug this in, you can use either one of these equations. You can use equation A or B. It doesn't matter which one. My suggestion is pick the easier one. My opinion would be equation A might be a little bit simpler, just because I have denominators of only x and y compared with 2x and 3y. So I'm going to focus my attention on equation A. I just called it equation A so that I could talk about it, which is 1 over x plus 1 over y equaling 7/12. And we're going to use the information that we know of y equaling 4. Okay. My little preference before I even substitute is to clean up this equation as best as I can. I'm going to clean it up by getting rid of the fractions, which you've seen me do a couple of times already in this video. I'm going to multiply everything by the common denominator. Now I'm looking for a common denominator between all 3 fractions. So common denominator between x, y, and 12. That becomes pretty obvious. The common denominator would be 12xy, right? All 3 of them. Okay, this is not a necessary step, but in my opinion, it does help clean things up. So when I distribute this through, this x will cancel out with this x, so I'm left with just a 12y. And now I have 12xy multiplying with the 1 over y, which now the y's will cancel. So I'm left with a 12x. And then here in the right-hand side, I can see the 12's cancel out, but now I'm just left with the 12xy. So this to me is just a little bit more of a friendly equation because of the lack of fractions. So now I'm going to take this y equaling 4 and plug that in. I need to plug it into a couple of different spots, don't I? I got 2 y's. So I would have 12 times 4. Again, I'm just trying to show those steps of substitution. Oops, equaling 7x times 4. So I would get 48 plus 12x is equal to 28x. Solve for x. We got 2 x's on either side, so I'm going to subtract to combine those like terms. What would that be? 16. And then we go ahead and divide. X is equal to 3. Okay, so that is question number 5, which means that final answer for this system of equations would be the coordinate point of 3, 4, right? We got the x and the y. To remind you what this coordinate point means graphically for this system of equations is that if I graphed equation A, right, you can use Desmos, you can type that equation A in, new line to type in equation B. If I looked on the graph to see their point of intersection, this is where those 2 graphs would cross. This would be their point of intersection. Okay, that actually is going to help you with question 6, which is asking you to describe how you would have solved this system using technology or a graphing device. So you're welcome to explore around in Desmos and that, but I will be looking for specific vocabulary such as point of intersection and how you can type these into the equation, what your domain and range would be to be able to see an accurate graph. That would be good to include. Yeah, so that should clear up for questions for lesson 3.